Hey, welcome back. Little project today. This is a Multifix A grooving tool holder. This is basically an ancient style of grooving holder, which takes a high-speed steel blade with a trapezoidal cross-section. As you can see, this is a dovetail slot, and it gets clamped here. And it's a fairly narrow high-speed steel blade, like about 10 millimeter wide, and they work for grooving, but for grooving I have better systems. I have the inserted carbide tooling, and I can grind custom tools, but this one is basically useless for me, and I think I don't even have a parting blade for this, or a grooving blade. So what I did, I went on the internet and I ordered a very narrow inserted parting tool. This is a 1.7 millimeter wide parting blade with a 2.2 millimeter insert, carbide insert. They come in different flavors. This is a steel insert, but there are also inserts like this one with ground and polished edges and surfaces, which are for plastics and aluminium. And these inserts sit in a double V arrangement, a V on bottom and on top, and they are slightly tapered, so they wedge themselves in until they hit the backstop. Usually you give them a little bit of a whack with a soft-faced hammer until they go in all the way. And to get them out, you have this wrench with this cross-section here, which goes in here, and you just bloop, pop it out. So there's the insert. It goes in like this. Then you give it a whack and drive it in. This obviously doesn't fit, so some modifications will be needed to do this. Yes, I'm fully aware that you can buy an AXA multifix for parting blades, and there is also at least one import reseller who sells parting blade holders, but I don't buy these holders from importers or resellers. So if you want to write that comment, sorry, I'm not interested. And I have this one already, so I'm going to modify this. These are usually at least case hardened. Let's find a file. Let's find a needle file. Crappy needle file. Ugh. Yeah, this is nice and crisp. We have a clamping arrangement down here, but we'll see if this is good enough for inserted parting blade. Otherwise, we have to modify the clamping too to have a clamping from above down. But I have an idea for that too. If this clamping from down below doesn't work, so we have this clamping shoe cut out. There is a spring in here, keep it under tension when you loosen the screw, and a high strength screw to pull all this mess together. I already scratched a line on center height. I just put the tool holder into the lathe, and I put a piece of carbide ground to a point in the spindle, just scratched a line. This is center height of the spindle, so when I put this tool in here, I need the carbide insert to be at this height or below, so I can adjust it up. Because when I scratch this line, I put the tool holder in all the way down, the lowest it goes. That's also the reason why I'm going for a 19 millimeter blade. These are sold as 19 millimeter, even if in reality they are a little bit less. These blades also have double V arrangement. So this is the arrangement this blade has, if you look onto the front. And this angle here is... So this is the parting blade I bought. Hoffman Group is the shop. This is the article number. Parting blade, steel body, 19 millimeter height, 2.2 parting width. CAD file, cutting data, and here's a sketch of the cross section. The height and the angle is 150 degree between those two angled surfaces. So this is not correct here. From here to here, it's 150 degree, like this. That means, so a full angle would be 180. 180 minus 150 is 30. So this is 15 degree from here to here. So, and the idea is that we have a little bit of an undercut in here with these 15 degrees. So the blade gets pulled tight up against the face and cannot slip out. When I said that this is going to be a simple project, I wasn't lying. We just need to mill the slot wider and grind the dbit. And I think the dbit is the only real reason why I'm making this video. Otherwise it would be just milling a slot. That would be making a video for drilling a hole. But as this is a simpler project, we can go into a little bit details here. A set of parallels. Get this in here. Oh, this is... So this is able to tip a little bit because the backside here has no flat surface due to the shape of the multifix. We're taking only one parallel and grab this holder way deeper in the vise like this. So it aligns vertically on the fixed jaw, so it doesn't sit like this or this. When it's up that high, it doesn't align as well on the fixed jaw. When you drop it down, it does. So one parallel, drop it up against, and we give a little bit of drag on the vise, so we can still kind of move it, but it's in place. And for this orientation, side to side, we'll dial that in. Get a little bit of preload. This is a 2 micron indicator, so this is fairly this is a bumpy roller coaster. So we start here at 0. And it climbs. It climbs fairly significant. It even over travels the indicator. So what we're going to do is we'll get a little bit of a pry bar below the part. A small brass pry bar here. And I will move the table slowly. And you can see it drops off, and I will just use the pry bar down here to raise the part a little bit. That's like a 3-hand affair. We're at 0. Okay, that's already better. So we start like 100 back here. And now we take our pry bar and we lift it a little bit. It doesn't need to be like 2 micron end to end, but it would be nice if it was within 10 micron. Raise it a little bit. Yeah, that's okay. I like that now. Let's tighten the vise down. We'll move a little bit. Okay, let's start here at 80. Okay, that's darn good. I like that. Drops a little bit, but with that surface finish, hard to tell. And if it is really like 10 micron over this distance, that's really not a big deal. By the way, for those who have never seen it, I don't use a magnet indicator holder on my mill very much. This is part of my solid indicator stand that I built, that I have a video on. And I just mounted a post, a 60mm post, solidly to the head of my mill, and I can put this indicator holder on there. And that's way nicer than having a magnet base. Magnet bases tend to scratch the surface you mount them on. They can start to tip over time if they get dinged up or if there is a single chip under it. This doesn't tip. There is no way to, when you tighten the screw, it's locked. Okay, that's the end mill I'm going to use, or at least try to use. This is a 6 flute carbide end mill with a coating for hard milling, and also a geometry for hard milling. The flutes are not very deep. The core of this end mill is very thick, so this is a reasonably stiff tool. So I'm using a 5mm dowel pin to touch off the height. So I dropped the cutter so the pin doesn't go under the cutter. Now I'm slowly raising the quill until the pin goes through there. There it is. Okay, now I hit just the diameter of the pin, in this case 5mm, into the DRO. When I crank the quill down to 0, I should be reasonably precise at full depth. But I will stay like 0.2mm off the floor right now. Now I just want to widen the slot. Okay, this is cutting quite well. This is definitely hard, but not stupid hard. And that's probably only case hard, but we'll see once I go in deeper. You notice that I climb cut. This is preferable. Climb cutting is always preferable, but it's not like a manual machine like this. It's not always possible. But I'm only stepping in 0.5mm or 1mm in next pass, and that's not hurting anything on a climb cut. Okay, that's a 1mm wide cut at 3000 RPM. Now as we milled out the slot, we need a cutter to create this 15-degree undercut. And the easiest choice is a dbit, a single flute cutter. Something like this. This is a large 90-degree, almost like a countersink, I think I used this to mill a large chamfer. Take a piece of carbide or high-speed steel if you feel a bit vintage. Split it in half, exactly to half the diameter. And you grind your shape, cylindrical grind it, basically. And then you grind something like 15 or 20 degrees of back clearance behind the cutting edge. That's this facet here. Then you roll off the remaining material from the end of this clearance. So the clearance drops off until here, then it's just cylindrical clearance. Or in this case tapered because it's on an angle. So that's what we're going to make, just with different dimensions. Already found a piece of carbide, carbide drill with 6mm shank, good quality. And we're basically, if I can find a bloody pen, I'm going to make a cutter that looks like, that's the shank. Like this. A very weird dovetail cutter with 15 degree here. So that's basically this view. Now when we flip it over 90 degree, we get like this. That's a cutoff line up here. A shank, and the split. And here's the undercut. And this split is exactly on center line. The reliefs are of course not drawn here, but that's what we're going to grind on the dbit grinder, so hold on to your hats. Okay, we're at the dbit grinder and I'm setting up to split the carbide in half. And if we do this right, we can make it a little bit easier on ourselves. One thing, the dividing head here is 3 positions. Indexing every, I think 15 degrees. Then you can set it to 180 degrees. This locks the motion to 180, and you need this to roll the back relief. And you can set it to spin freely altogether if the handle doesn't get in the way. You can free spin. So the way we start grinding, we can make it easier ourselves. Let me demonstrate to you with this piece of blue tape. Go to, this is now our 180 degree motion. This is what's used to grind the back relief. And when we're at the left, extreme left position, we want the flat of the split we grind to be horizontal. So the back relief starts there. So we basically want the split to be like this. And then we roll off on the back. That means that we go to this position to grind the flat, to split the carbide blank in half. Then we move over 90 degrees and lock our rotation to 180 degrees. This is really hard to explain. Then we can, in the same setup, roll our back relief, our back clip. Every other joint here is set to 0, everything is locked. And we're good to go. We rough position this fellow here. I'm using a diamond wheel. D125 is the grid. There are conversion charts for mesh size or whatever other grid designation you use, but here in Europe the D for diamond and B for CBN wheel is the common grid. The smaller the number, the finer the grid. It's fairly easy. So safety losses. So we get our dust chute below, because this operation creates quite a bit of carbide dust, about half the diameter of the carbide blank. And now we just traverse in and swivel the tool back. I'm going to grind about, I don't need very much. I'm going to grind like this, maybe split about 6 millimeters off the blank in half. One little trick, you cannot adjust this the graduated ring on here, the dial. You cannot set this to 0, but what you can do is you can crank it to 0 and then use this upper dial to move the whole spindle assembly. And this moves the spindle back and forth, and you can use that to 0 to touch the grinding wheel against your carbide. Okay, here is our carbide blank split in half. Yeah, we're like 30 microns over, but it shouldn't be an issue in this case. I'm not going to fool around with this forever. Now we need to grind the 15-degree back taper, which is our dovetail shape. For that, we on the Chinese dbit grinders, at least on most of them, down here is a pin, and once you loosen the lock on this side, you can swivel this guy and you can move up to this pin, and this is your hard stop for 90 degree. It's also adjustable, it's eccentric, and there is a set screw. When you loosen this, you can set this to your desired 0. So we can go 15 degree, but that's the wrong 15 degree. We need to go the other direction, and for that we can take this pin and pull it out, and then we can basically move wherever we want, like this. The only problem in my case is I don't have the graduation stop at 0, so we can loosen this dial here, move it to 90 over here. And now we can take our 15-degree back taper and lock it. Down here we set the back relief for the OD. That's important so the cutter doesn't rub. 15 to 20 degrees for a dbit is a good choice. I'm going for 20 degrees today because, well, I feel like 20 is good. Then we move this whole workhead closer to the grinding wheel once again, like this. We make sure that we have a lot of travel left, not a lot, but that we have travel left in this bar down here because this has only about 10 to 15 millimeters of travel. And then we set our 180 degree stop like this. And now we just move in and grind like this. This will create the correct back clearance and also the 15 degree back taper that we need to cut our shape. Okay, there we go. That's the 15 degree back taper and also 20 degree back clearance. You can see a little bit of a facet down here. That's the back clearance facet. So next we just need to grind a little bit of clearance on the front, but we can do that offhand. Take your cutter. This side out here, this is the cutting edge. So we go in contact with the grinding wheel, we tip it back and we tip it over like this, and then we just grind until we're at the tip. Again, very easy. And there we go. There is our 15 degree dovetail cutter. Front clearance is plenty. It's not going to be an issue, but usually that's good enough. You could also move the whole workhead around and grind the front clearance with the machine, but usually I just grind them offhand because it's a little bit quicker. Okay, here's a close-up of the cutter. That's the split surface. This is basically from here to here, 3 millimeters. That's the 15 degree back taper. It's hard to tell, but there is a facet. This is not completely ground around, but there is a facet, and then there starts the rolled off surface. And the front, as I said, it's just cleared in this direction and in this direction. The clearance angle on the front are obviously way overdone, but it will do fine. It will cut very nicely. Okay, we're back at the mill. Set up the cutter. Set up the cutter in the spindle, held in a collet, relatively short, running at 3000 RPM, and I'm going to use a little bit of blue marker on here so we actually see what we're doing. So let's take a little bit of a cut. Okay, let's proceed on. I went 0.2 millimeter deep in. I'm going to take the same cut on the other side of the slot so my dovetail stays symmetrical in size. This is now trial and error until we get a nice fit on the blade. It doesn't need to be crazy tight because we're actually clamping it up against the upper surface. Oh, there we go. Oh, that's almost spot on. A little bit tight. I'm going to take like 50 micron more. Then it should be a nice sliding fit. Oh yeah. Oh yeah, I actually like this. I'm going to keep it like that. From this side, yeah, that's nice. I'm not sure what the tolerances on these blades are. Probably if I buy another blade, it will be completely off. But well, that's just life. But yeah, this is nice. I hope this works nicely on the machine too. Well, that's a beautiful finish. Okay, got the milling done, and put it back together, and tried it out on a lathe. And it seems to work. It seems to work very nicely. I was a little bit worried that the way this blade is clamped with the screw from above and the blade being pulled up against this upper edge of the slot, that this might be too fragile or too flimsy for insert a parting blade. These parting blades have significant cutting pressure because the insert has a very robust geometry. We will look at that in a second a bit closer. But still this is an M6 12.9 screw, a high strength screw, and this is designed quite nicely, and this seems to be rigid enough to do parting in steel. What you saw in the short clip was a piece of 35 millimeter C45 0.45% carbon steel. Let's look a little bit closer at the fit of the blade in the slot. Okay, close-up time. This is the parting blade, this is the slot, and this in here where the blue paint is removed, that's the dovetail undercut that we machined. And you can see that I need a pointer. Down here, this is the backside of the roof shape on the blade. This clears down here, but up here, this short section of the roof shape mates up nicely with the dovetail. That's what's giving the clamping or holding power. So that's working quite nicely. That's a nice fit. And when we turn it around, and when we look at the insert, that's the insert in a close-up view. This line here in front here, this is the cutting edge. By the way the light reflects on this edge, you can tell that this is not a sharp edge. This is definitely a radius. Now you can see it way better. If this was a sharp edge, you would not see this bright line up here. This line up here, you wouldn't see this if this was a dead sharp edge. So that means there is a radius, an edge prep edge preparation. And that's done to make the cutting edge last longer and be stronger in general. Because a sharp edge is more fragile than if you round an edge over. Also, we have this geometry in here. This is to deform the chip and make the chip narrower than the slot we cut. And last but not least, it's a negative geometry. This small facet in front here, this drops off to the front with a few degrees, and this creates a very, very strong angle between here and here. This looks almost like 90 degrees, and that's super robust. The problem is negative geometry takes way more force to push it into the material. So there are pros and cons to this geometry, but in general these inserts work very nicely. And if you have problems with the cutting pressure, you can always come in, go on a grinding wheel and grind. We have accelerated grind a chip breaker like this with a highly positive geometry. That will make the insert cut super free and still roll a nice chip out there. But the insert gets more fragile that way. But still, that's always an option. It's always an option to modify inserts. Okay, here we go. Final parting tool blade. I did some deburring and corner rounding on all the milled edges, but that was a nice little modification to this otherwise to me useless multifix holder. And as I said before, AXA makes a holder for parting blades like this with 3 clamps from the top. That's definitely superior in rigidity over this one, but it costs money, some real money. And one importer or reseller here in Germany also has a made in China holder for parting blades, but I prefer the AXA holder here. And this little modification was not too bad. Mostly I filmed it to show you grinding off the custom dbit to cut the undercut, the 15-degree undercut. So I think we're done here. Thank you all for watching. Thanks for the ongoing support, either by email comments or monetarily on Patreon. Stay safe, and I'll be back.